What do you reckon the most common incorrect answer is? What's C? Oh, no. No, it's the most common incorrect answer for a BC test would be people that know stuff that make that. For A and B, it'd just be some crazy randomness. So the most common is actually D, the distractor common. And that's because people take the derivative, 1 minus 3x squared, they isolate, and they say, oh, it's vertical if y equals 0. So that's only got one solution, so 1. And people go with D. Is that true? No. Of course not, because when y equals 0, x could actually be 3 different things. Do you agree? So there are 3 solutions to this, and the answer is B. Alrighty. Let's go to Tricks Up Part 2. Here you go. Are you ready? This is some fun, higher level thinking. Yeah? This is a perfect blend of you with your fancy, amazing minds and a great challenge. It's like a Ferrari on the autoboard. Taking your little Ferrari of a mind on a perfect course. There it goes. So Tricks Up. Yesterday I talked to you about, I told you what you saw when you do it. Yeah? Now today it's up for you to know what to trig sub or how to trig sub, what to choose. This is the basic idea. 1 minus sine squared is an identity. So if the problem involves 1 minus x squared, if you see subtraction in the function second, you would probably use sine. If, however, let's say this, tangent squared plus 1 is an identity, now that would be used anytime you had a squared sum going on in the problem. So if I solve x squared plus 1, I would let x equal tangent. Secant squared is an entirely different identity, and it involves square function minus 1. So if I saw x squared minus 1, I'd probably use a secant substitution. Now notice that none of these involve, you'll never see using cosine for a substitution, or cosecant, or cotangent, never the C's. We typically do that. Cosine, cosecant, and cotangent not typically used if for no other reason than because they involve negatives on their derivatives. Cosine could be used anytime sine, because 1 minus cosine squared is an identity too. But then the dx is negative, and it's just easier, okay? So, the main substitution facts are either tangent, sine, or secant. The problem, though, is if it's not just a straight up, actually, let's just see how this works. Say we didn't remember what that antiderivative was. By trig substitution, you would say, well, I know an identity is tangent squared plus 1 is nice and clean, yeah? So you could let x equal tangent of theta, in which case the bottom would become tangent squared plus 1. dx is secant squared theta d theta. Well, what is tangent squared plus 1 in the denominator? Secant squared. Secant squared and secant squared go away, so that's just 1 d theta, which is theta plus c. And what is theta? If x is tangent theta, then theta is arctangent of x. Okay? Now, that said, then you could always, even if you didn't remember anything, if you just remembered identities, then you would be good to go. So let's take a look at these. Now, I'm not having you do the whole problem. I'm just practicing the what would you sub skill. So this, ignore this, the squared sum or difference, that's where you look. That's the start of the show. That's what decides the substitution. which one would yield an identity? Sine, tangent, or secant? Sine, all right? So I know that y needs to be some kind of form of sine, and now we deal with the 5. So you first choose the trig, and then think about how to deal with the numbers, the constants in there. Now, I would love for it to not just be sine here, because 5 minus sine squared isn't an identity. I need something there that's going to match that 5 so I can factor out the 5. So it needs to go in front. Yeah, you would need after squaring to be a 5, so it needs to start as root. So x needs to be root 5 sine theta, so that when you put it in, not x, sorry, y, excuse me. Y needs to be root 5 sine theta, so that when you put y squared in, you're getting a 5 sine squared theta, you've got a 5 factored out, you've got your identity, boom, you're rolling. You with me? Let's try another one together, and you can try the other two on your own. All right, so here I see a squared sum. What should I use? Tangent. So I'm going to go with some kind of tangent. Now, in this case, I actually want to do two things. I want to get rid of the 25 and match the 2. I want to dump the 25, match the 2, so I can factor out a 2. So what would I put with the tangent to cancel the 25 out? 1/25? 1/5. Which one? 1/5. Because we're going to square it, it only needs to be over 5, so that when x gets squared, I'd have tangent squared over 25. 25 drops out, right? Now, I'd also like it to have a common factor of 2 after squaring. So before that, I need to make it root 2. Now, you will, when you do these problems, the very first thing you're going to do is put that in, and you'll be verifying that it works. So if you did the next step, it would look something like 25 times x squared, and x squared would be normal 2, tangent squared, 25. The 25's drop out, you've got a common factor of 2, tangent squared plus 1 is an identity, we're good. You follow? All right, try the other two, please. Clarify what checking. Okay, so for the last one, did you choose tangent? Yes. And what constants did you use? Root 23 in front and root 3 in the denominator. That does work, I think you'll find. And you do get identity, tangent squared plus 1 is secant squared. All right, you with me so far? All right, then, let's do this a whole problem. Now, I guess it would be logical to say, hey, it says integrate using trig substitution. The notes are about trig substitution. You're thinking trig substitution, but step back and think you're taking a college placement test, okay? And it's just a mixture of problems, and you're trying to figure out how to integrate this. Your integration or trig sub is a great skill, but your primary skill is it a known derivative? U sub is the second most important skill of all integration. This is not a U sub, I think you'll agree. So you would only use trig sub after checking off a few boxes. Is it known? Is it U sub? Then you'd say, oh, maybe it can work here because I do have a square and a difference. Trig sub's good, possible, right? So what shall we make x? Secant, and what about the constant I need to throw in? 3 in front or 3 below? 3 in front. Now you should always go to the root first and make sure your substitution works before you go wasting your time finding the dx and everything. First, make sure your substitution gave you an identity. Does our substitution pan out? Yeah, I'm going to get a secant squared minus 1. That is an identity for tangent squared. That's the whole purpose. I think that's the correct thing. Now let's find the rest. What is dx? Three secant theta tangent theta d theta, and x squared in front in the denominator is 9 secant squared. All right, let's do some cleanup. What is the overall constant out front of the integral? I agree with 1/9. The root will give a 3 that'll knock out that 3, so 1/9 seems right to me. Okay? Doing a wee bit of cleanup, a secant will drop out. Keep the tangent in the numerator for a minute. What about the root after identity and square rooting? What is it? It's just tangent, yay? And I still have a secant down there. Do you agree? Okay, I lost a secant. I have tangent over tangent, so at the end of the day, 1/9 of cosine. What's the antiderivative there? Sine. 1/9 sine, and is that good? Circle it? No. What else do I have to do? All right, you need to sub back for x. If you take this fact and make it a ratio, trig equal to a ratio, from that you get a triangle that relates all the components. What is secant the ratio of? Hypotenuse over adjacent. So the hypotenuse is x, the adjacent is 3, therefore the opposite is root x squared minus 9. And we're ready to do sine. What's sine? Root x squared minus 9 over x plus 6. All right, that's what trig sub looks like in its entirety. Are you with me? Try the other one. It's on your own. Are you? All right, how are we doing? Are you done? So, do you have x over root 4 minus x squared to start with? Then you have inverse minus inverse sine of x over 2 plus c senior. We good? How'd you do? Okay, let's go to some other variations on the p. Sometimes you'll see a problem like this. Again, I would think u sub, it's just not going to happen. Your u is, I guess it's easy to choose a u, but you have no du max, so the u sub's out. There's just, it's a mess. There's no way to do it, so that's where trig sub comes in. You could, I imagine, somehow get a sum or difference of squares, but you would have to make it yourself, because there definitely is not one right now. So the first thing you're going to do is say, forget the square out front, that's not the issue. You want to, in here, make a sum or difference of squares. So think x squared minus 6x, and leave a space. And push 11 off to the side. Yay? You follow? Okay, so what goes in that space? 9, and balance with a negative 9. What does the base of the square, what does the inside of that square look like? It's down. X plus x minus 3, not plus 3, x minus 3 squared plus 2. Yay? Now it's looking like a sum of squares. Now we're talking. What substitution should we use? Sum of squares. Just think blank squared plus blank. Tangent. Okay, so x minus 3 equals tangent theta. Now, that would be great, but if I squared that, I would have tangent squared plus 2. That's not negative. So this then goes to that, got to knock out the 2, or deal with the 2, or match the 2. What do I do? Root 2 in front or below? In front. So that when I, oops, do I want that on the x or on the tangent? Okay, my bad. So that when I put in for x minus 3, I get a root 2 tangent squared, which is 2 tangent squared plus 2 all squared. I think that'll be good. Once I take out the 2, I'll have an identity. We're cool there. So what about the dx then? Does the minus 3 affect the dx, the derivative at all? No. No. Okay, so dx is just? All right. You with me on the substitutions? The overall constant out front is root 2 in the top and 1 in the bottom. 2 or 4? 4. Once I factor out the 2, it has to get squared, so it's a 4. Secant squared is cool in the numerator. What does the denominator become? secant to the fourth, but I think you're a step ahead of me. When you have secant to the fourth, two of them will go away, leaving you with two secants in the denominator, yay? How do I deal with that integrand? Cosine squared. How do I deal with that? 1/2 plus or minus, which is plus 1/2 plus 1/2 cosine of 2 theta d theta, the antiderivative of which is 1/2 x or theta, theta, plus 1/4 sine of 2 theta plus c. Am I done? No. We need to sub back 1/2. Way back here, this implied as a ratio x minus 3 over root 2 equals tangent theta, yeah? If I isolate the trig statement. Theta is the angle. What sides are being given? Opposite is x minus 3, adjacent is root 2. The hypotenuse is pretty gross, but what is x minus 3 squared? X squared minus 6x plus 9 plus root 2 squared. So x squared minus 6x plus 11. Does that look familiar? Yeah, that's in the original problem. That'll all happen. It's all traces back to them. So theta then. What is theta? Arctangent of x minus 3 over root 2 plus, oh man, I don't see theta. Can I just double everything to get 2 theta? No, that's ridiculous. Okay? You can't do that. After all, is the sine of 90 2 times the sine of 90 180? No, I mean, that's sine of 90 is not 2. That's crazy talk. So what do we do? 2 sine theta cosine theta. You use an identity to get sine cosine thetas. And then I can see the finish line. I power through with a sine theta of x minus 3 over the square root of x squared minus 6x plus 11. And a hypotenuse or a cosine of 2 over x squared minus 6x plus 11. Now, I can assure you, checking your answer to these in the homework is no wonderful chore. I'm going to be asked constantly, I don't know if I did this right or not. I got an answer, and I think I did it right, but it doesn't look like that answer. We could talk about that. But that is going to be a hard part, verifying your answers. All right, last but not least, there are lots of uses for trig sub. It just opens the door to a million different integrals that you otherwise could not have done. But one big use, just touching on one use, is it allows you to get secant cubed. Now, secant cubed is a pretty famous integral. Here's why. If you consider arc length is the integral of 1 plus f prime squared dx. We've been using our calculator for those, and we still will for some of them. But depending on what f prime is, you could definitely see this happening to be something like a little trig substitution. Now, surely it depends on what f prime is, but you could say, which trig sub would you use? Tangent. You would use tangent, and the derivative, again, it depends on what f is, the derivative would be, but my point is you would often, from an arc length calculation, get secant cubed, because the 1 plus tangent squared would be secant squared, square rooted is secant, but then times the dx is secant squared, so secant cubed happens a lot in arc length problems. Not every time, but many times, all right? Now then, secant cubed requires some major skill on your part to integrate. I know it seems like we've done powers of trig to death, and you can do every one, but no. Secant cubed requires you to put two calculus skills together. integration by parts in what's called circular integration. It's fun, you'll love it. So let's start here. Secant cubed. Do you have any ideas about how you might approach? Split it, yes, very intuitive. Now it's important that you write the left side. Treat it like an identity where you're going to be constantly working the right side while the left side stays there because, well, you'll see. Oops, I just changed it. It's not there at all. All right, so split it. I like it. Any other ideas? Identity, I heard tangent squared. Tangent squared, is it tangent squared plus 1 or minus 1? Plus 1. Like it, I like it. Okay. So now, you get tangent squared plus 1, secant squared. You follow? And what then? Distribute. Tangent squared secant. Yeah. I feel like this isn't going. Yeah. Everything you're doing is fine, but it's going to be a brick ball. So I'll scrap that and go back to here. That was a non-starter. All logical things. So you didn't break any math. It just doesn't go anywhere. Sorry about the erasers. Think of a different thing to do. Not identity. Use integration by parts. Okay, now that's not totally counterintuitive because secant squared does lend itself pretty well to ultra by the voodoo, yay? So what shall we let u equal? Secant and dv. Secant squared, and therefore du. Secant tangent and v. Tangent, all right? So this then becomes secant uv is secant theta tangent theta. And the integral of voodoo is tangent squared secant. Are we good? All righty, now we're cooking. What about tangent squared? Secant. What can you do here? Identity. Now think identity. Identity. Secant squared minus 1 for tangent. Yay? You follow? Now that then becomes secant theta. Oops. Secant theta tangent theta minus the integral of secant cubed theta, and then minus secant integral or plus secant integral? Plus secant integral. Now that's pretty great because you're right back to where you started. Isn't that awesome? But more. You're right back to where you started plus more. Isn't that great? It's actually quite awesome. Now what do? You can bring the relation. Bring it over. So now you bring it over, and you get 2 problems you don't know equals something you do. What is the antiderivative of C? Maybe you don't know. Natural log of, absolute value of secant theta, tangent theta. Hold off on the plus. I'll put it in at the end. So surely then we didn't want to find 2 secant cubes. We wanted to find secant cubes. So how do we find our final answer? Divide by 2. So it is 1/2 divided by 2. Secant tangent plus log of secant theta plus tangent theta plus a c at the end. That's called circular integration with the side of integration by parts. Okay, it's pretty great. quickly break. Your hope is to get right back to where you started. All right, that is that. Every time I say, do we even have to be able to do that? The answer is yes. Yeah. Okay. Question on 112. Questions on 112. 25. 25 is a good question. 25 is a little abstract. 16. Okay. 21. Okay. Okay, so as abstract, as wacky as it is, they're actually making it much, much easier on you that they get you started. And some textbooks, they're heavy on theory, like you might, I don't know, the University of Chicago is super heavy on theory. You would just be given prove 0 to the infinity is indeterminate. That's it. That's the proof. That's not easy to do. They're getting you started. They're saying, let f of x to the g of x be such an indeterminate form so that you can ensure, or you can assume that f of x is going to 0 and g of x is going to infinity. Supposed to use accepted math to prove this. This is an indeterminate. I don't need to take derivatives. I don't need L'Hopital. I can know what the answer is, period. All right? So if you do the old exponential work like we have been doing, e to the log of f of x to the g of x, and then make that same second step, bring out the x, or the e rather, and bring down the exponent. All right. You follow me? Now, on 0 to the 0 problems, if I were at this stage, then I would have 0 log of approaching 0. Log of approaching 0 is negative approaching negative infinity, and I get an indeterminate form, and therefore I have to get into the rates, right? Likewise, if I did infinity to the 0 and got to this stage, I would be 0 log of infinity. That's 0 times infinity. That's an indeterminate form. These, as well as 1 to the infinity, those are all indeterminate forms once I get to this stage. But look at this here. We said, by definition, that g is approaching infinity, yeah? And I'll hang on the log for a second. F is approaching 0. Now, I am going to argue that that is not in any way indeterminate. What is log of approaching 0? Negative infinity. And what's infinity times negative infinity, or huge numbers times negative huge numbers? Is that I don't know, or is that I know? Yeah, that's I know. That's 0 every time. That's not indeterminate. Okay? Now that actually makes sense if you think of this now. Go back and think of this numerically. Think of approaching 0 to the infinity. 1/10 to the 100. 1,000 to the 1,000. Aren't those going to get stinking small? That's not, I don't know. It's definitely going to 0. Okay? It's, and this helps a person understand, yeah, that's got to happen, but it's not proof. Okay? All right. Does that make a little sense? I gave him a best shot. All right. 16. That's 16. 16, this is definitely a case of people are making this too hard. I am here to say that once you get practice on these, you start to feel more comfortable. These are not. First, converge or diverge is all about what's the limit as you go down the list of terms, yay? I'm going to clean this up and call it 1 over root n. First of all, because it's not a L'Hopital problem anyway. You don't need to do L'Hopital on series problems or sequence problems. You can use end behavior. And it's a heck of a lot easier to think of what does this do than this, yeah? Next is I had a dozen questions in the last week or so. Yeah, but what about this thing? I don't know what it does. This thing goes to infinity. I know. What's the limit do? I don't know. Doesn't matter. Doesn't matter. Okay? If I put in n equal 1 to start, I get 1 over root 1. Then negative 1 over root 2 when n equals 2. Then I get positive 1 over root 3. Negative 1 over root 4. Positive 1 over root 5. Negative 1 over root 6. That's not hard. Where do those go? The negative, does it matter? No, it doesn't matter. Yeah, they're bouncing back and forth, but the number is getting smaller and smaller. It doesn't matter. It's going to 0. Period. And it converges. Okay? So don't overthink it. And do think numerically. I do not need to see L'Hopital. Okay, on sequences. 21, is 21 still a question? Yes? No? Somebody asked 21? No, you're good? Okay, cool. Thank you for letting me know. All right, let me know if you have any other questions. Yes?
Not a core, but just like, you have to get dy over dx for trigonometric rectangles,
Gotcha. I blew that part off the last question. So yes, I'm down. I can show you what I guess I'll show you what I want to see really. So you know x is 3 cosine and y is 4 sine, and when you eliminate the parameters you have this. And if we do this in terms of theta, dy d theta is 4 cosine theta over 3 negative 3 sine theta, yay? Okay. And if you do dy dx here, sorry, give me a second. You get something like negative 2x over 9 times 8 over 1. That doesn't, that's what I thought. What's going on here? Did I make a mistake? Negative 16 over 9. That's kind of cooking me out, man. Did I make a mistake? Oh, there's a y there, yeah? Okay, are we cool? All right, so here's showing these are the same. Show they're the same. Think in terms of x. What is x equal to? But 3 cosine theta, yeah? And what is y equal to but 4 sine theta? And so I do indeed get something like negative 4 cosine over 3 sine. That's kind of what I was looking for, some kind of substitution to show that these derivatives, though looking different, are the same by substitution. Excellent. Does that make sense? The derivatives look differently, but they're the same. Okay. Let me know if you have anything else.